Just very briefly, welcome everybody. So today the seminar will be hosted by Jonas Jäger. He's currently a PhD student, basically finishing in University of British Columbia, expert in a bunch of quantum machine learning topics, and he kindly agreed to give us a seminar about his recent work. So yeah, please.
Yeah, thank you very much, and thank you very much for the invitation. Yeah, it's very exciting for me to talk about this fairly recent preprint. It's like the first time giving a talk on this paper, which was published in the archive about a month ago. And yeah, it has the title Provable and Scalable Quantum Gaussian Processes for Quantum Learning. And yeah, I guess I will get started right away. So the main issue with quantum machine learning is that it has recently, even though it's hasn't been around for that long, encountered many roadblocks. So for example, originally it really kicked off with like using quantum linear algebra primitives, such as the HHA algorithm, but this really had like limitations in terms of the classical data access. And then more recently, and also a topic I'm more familiar with, is variational quantum machine learning, where we use parameterized quantum circuits. But they have a bunch of issues, like they're difficult to optimize, and you very quickly end up with these phenomena like barren plateaus, or like in general like exponential concentration phenomena. So in addition to that, many quantum machine learning approaches are not really naturally suited to deal with quantum data. And quantum data QML will be the focus here. So what do I mean when I say quantum data QML? So this means that we, instead of classical input vectors, we now have quantum states as the input. We come from some quantum system. We assume that, and this is why we use machine learning then in the first place, there's some unknown unitary transformation that transforms these input states. And then there's some observable O, and we're interested in learning the action of U so that we are able to predict expectation values here yi corresponding to the input quantum states rho I. And then, oops, sorry. I think, can you still see?
No, I can't see to black.
Now it should be back.
Now it's good, yes.
Okay, perfect. Sorry. And yeah, so this forms our quantum data set. So it's a, tuples of quantum input states rho I and corresponding expectation values yi. So now, what is typically done is that we now define a quantum model, and this could be, for example, like in typically some variational or parameterized quantum circuit. And the main issue with that is that this choice is often made completely isolated from our actual task domain. And this often then leads to poorer predictions. And so maybe, like, if we don't really align our model with the task domain, with like issues that it might not be expressive enough. So for example, it might be not able to really capture the data very well everywhere, or it might lead to like artifacts like here in this area that result from like the model trying to forcefully predict certain training points, or most importantly, it might have issues with or like might struggle to extrapolate like here in areas where there's beyond the areas that or regions that are covered by training data. Overall, in more like machine learning lingo, this means that these models lack inductive bias. And this is because there's another important ingredient beside the quantum data set that should go into the design of a quantum machine learning or like in general machine learning model, which is task assumptions and domain knowledge. So this would then inform the design of our QML model. In our setting, if we have knowledge about the physics behind our quantum data set, then this would be a physics-informed QML model. And then hopefully with that, our training is well-behaved. So we have a well-behaved interpolation here, and the data is well fit. And even if the extrapolation still doesn't work as expected, we would have some like uncertainty quantification about the fact that the extrapolation is not successful there. And then this means that we have a strong inductive bias here. So now you may wonder, okay, how can we then convert domain assumptions or knowledge into a quantum model? And that's exactly the topic of this work. We do so by using quantum Gaussian process models, where we convert domain assumptions directly by encoding them as, or like by defining quantum kernel functions. And yeah, let me start with a brief overview of our work. So we define or we phrase a general quantum Gaussian process QGP framework or toolbox here. We propose kernels that correspond to different types of assumptions. Here, particularly in this work, we focus on a kernel or a QGP that acts on, or like that is based on assumptions where we assume a transformation acting on all qubits, and then we showcase this framework on applications. And these applications comprise regression, classification, and optimization. For the agenda of this talk, I will first cover this general QGP toolbox, and then in particular focus on this certain class of QGPs, which are match-gate or free fermionic QGPs. And then finally, we will look into some applications. Okay. Before we get started with the theory, I should maybe spend some time on background on what Gaussian processes are. So this is helpful to like understand the quantum version better. So in general, a stochastic process can be understood as a distribution over functions, and this essentially means that we have a collection of random variables at several input points, T1, T2, and there are infinitely many. In machine learning practice, we are typically only interested in like representing our functions as a finite set of points in terms of like training and test sets. Then such a stochastic process is a Gaussian process, which we can denote here as f of t being distributed or sample like this GP. And it is Gaussian if for any finite subset of these random variables, that these random variables form follow a multivariate Gaussian distribution. So,
sorry, to clarify, so you mean for different t, these are not independent, right? You're saying, or
yeah, I mean they could be independent, right? I mean they could be like the multivariate Gaussian process could be in a Gaussian distribution could be in a way that only the diagonals of our covariance matrix are non-zero, right? But it is important. It is important that for any subset that the distribution that they form is Gaussian, not like a different type of distribution, right? It could be, yeah, some other distribution. Okay. Then, yeah, we can. Well, it's very popular to use Gaussian processes for regression models in statistical machine learning, and especially because since they're probabilistic model, they come with uncertainty quantification, and it's because everything is a Gaussian distribution. It's rather efficient to compute these things. So everything can be computed in closed form. But what this means is that we typically have a mean prediction with a Gaussian process model, which so to say reflects the most probable function that corresponding to that we have the variance in addition, which is our uncertainty quantification. So this reflects how confident we are with certain predictions. And that's especially for like scientific applications. This is a very useful property. So now, how does Gaussian process regression work? So the this pair mu and kappa, which is our mean and our covariance function, or more commonly called the kernel function. This pair defines the prior. So this is all of the statistical knowledge that we have before seeing any data. And so this means a priori our predictions can be then just sampled from independently from these, just from a normal distribution with mean mu and variance kappa. And this is also why especially the kernel function here is so relevant when it comes to encoding task assumptions and domain knowledge. And then the training data or observations are also assumed to be normally distributed. So we assume that we cannot see the exact values, but we are only limited to some observations subject to some Gaussian noise, which is also very useful in terms of quantum, in terms of the quantum setting, because our expectation values we typically can never see exactly, but we are limited by some shot noise, which can be approximated by a normal distribution. And this shot noise here is typically, this observation noise is typically assumed to be independent, identically distributed noise. So then this covariance matrix just simplifies to a diagonal with the same variance terms in each entry. Now we combine all of this in a joint Gaussian distribution. So for a new point f of t, this is where we which we previously only had for in terms of the prior distribution. Now in this joint Gaussian, we also incorporate our labels y, and here you can see how the corresponding noise assumption comes into play here as this additional covariance matrix R. And then all of these matrices K are just matrices of kernel function evaluations of different points. And yeah, just like calligraphic T is our training data set T. Okay, now how can we learn from this training data? where we have this joint distribution, a Gaussian distribution over both, like the new data point prediction and our training labels, and learning now happens by conditioning on the training labels, and yeah, this is how you can. So this is then again conditioning a joint or like joint Gaussian distribution gives you again a Gaussian distribution, and this is then how your predictive mean and predictive variance are expressed. And to see some
the classical, right? Just to entirely classical settings. This is still entirely classical setting, right?
Yeah, that's still a classical setting.
And here, so it's like a very simple model where the only parameters to train here are these average and sigma. Just to
yeah, kind of. I mean, there's essentially not really much training going on. I mean, in some sense, Gaussian processes are non-parametric models. So we get like these like the learning is really in like closed form. There's no parameters being tuned. It's just by using
an estimator for them.
By using the labels and importantly here the kernel values of between training points and the kernel values between a training point and a test point.
Okay.
Yeah, and then so the this will typically then result in something that looks like this. So the more training points you observe, the more certain your model gets in these regions, and yeah, so the predictive mean hopefully aligns more with the ground truth, and the predictive variance reduces. Okay, so now let's transition to the quantum Gaussian process framework, and let's stay with the general setting for now. So I said before, when it comes to I introduced this QML with quantum data setup before, and now we should formalize how these assumptions I talked about. So as we saw before, the quantum data set is composed of the input states rho I and the expectation value observations yi. So now the assumptions are based on the unknown unitary transformation U and the observable O. For the unitary, we assume that it lies in some subgroup of the unitary group on global unitary group, so on the n-qubit system. And that within this group G, subgroup G, we don't have any preference. Then the second assumption regarding the observable is that the observable is also restricted to some subspace of the general operator space. And more importantly, that the subspace is invariant under the action of group G. Okay, so I will now show, first formalize or provide some more details on these assumptions, and then show how this contributes to obtaining what we call provable quantum Gaussian processes. So for the first assumption, in terms of the subgroup where the unknown unitary is assumed to be in, let's switch to a probabilistic perspective of this assumption of no preference within G, which means that any element in G would be equally likely to instantiate the unknown transformation U. And this is exactly reflected by a uniform probability. And then more formally, in terms of these a Lie group G, we use the harm measure to formalize this. So yeah, we write U being sampled from G according to the normalized harm measure. And this harm measure, as you might be familiar with, is uniquely defined by its left and right invariance property. If you're not too familiar with the harm measure, just think of it as a uniform uniform distribution, or like uniform sampling from this group G. And we often omit a specific label for the harm measure and only write the tilde. Now the other assumption on the observable subspace is that G is this subspace B prime is invariant under the action of G. So this is formally described by for any operator in the subspace and any element from our group G, when we the adjoint action of U on this operator from the subspace B prime will again be in any representation of G. And then this is this also means that G decomposes our operator subspace into such subspaces, and we also sometimes call these subspaces modules or G modules. Now, let's since we established this probabilistic perspective on our assumptions regarding U, we are ready to define what a quantum stochastic process is, and then can formalize what we mean that, or I will show how to prove that such a quantum stochastic process then actually a quantum Gaussian process. So let's say we have a fixed state family in observable O, and now we have a U being random according to the harm measure on subgroup G. So we simply obtain a quantum stochastic process here as with this expression. It's important that here the stochasticity, or like the randomness, comes from the fact that we sample U from G, and not like the randomness that we have from random measurements or anything like that. Here we assume just like exact expectation values for now, right? So there's no other source of stochasticity. And so we now have that for each fixed point T, this the corresponding function value is a random variable, right? As before when we talked about classical stochastic processes. So if this if this stochastic process is now Gaussian, then we simply refer to this as a quantum Gaussian process. And here it's important that our assumptions lead to explicit expressions of the mean and the kernel. And we can check for Gaussianity by checking that the odd moments are all 0. For this, we typically this is typically based on the assumption that a priori the mu is 0, so the mean is 0, and then so then it means for a distribution to be Gaussian, all of the odd moments have to be 0, and for the even moments, we have to check that they are fully determined by covariances, so fully determined by these kernel values, and they actually have to follow this specific form here, so that if you have the moment over these k points, so the kth even moment, this has to be expressed by the sum over all possible pairings of these k random variables, and for each of these variables, it is the we have a term here that is the product of these kernel values.
Sorry, can I ask you
Mm-hmm.
one clarification here? So T, what does it represent usually in this context? Like, do you think of it as actual time, or like represents an encoding of information in the states or something?
Yeah, it could be. I mean, most abstractly, you can just think of it as a label, right? But yeah, it could be time. So if your state preparation depends on some time variable, but yeah, it could be some other parameter or some abstract label. Yeah, but it's useful to think of it as time. Yeah.
Okay. And you said here you don't consider shot noise stochasticity. So when you say that FU is Gaussian, you mean with respect to fluctuations in the U, right?
Exactly. Yeah.
So what do you have in mind? Like random circuits with some parameterization? What does it mean Gaussian in this? Because Gaussian with respect to changes in the circuit, kind of. What does it mean exactly?
So here, because we define U to be not fixed, but randomly sampled from like how random from G, right? But this corresponds to our assumption, or like prior assumption, that U could be any element of this group G.
Right.
Yeah, I will show an example in a second.
Okay.
But yeah.
Sorry, but the observable O is fixed.
Yeah, the observer is fixed, and the also this like state family, or like the the form of row is also fixed. Yeah.
Okay.
Yeah, and sorry for this typo here. This should be a J and J prime. Yeah, but this is generally the way how you can check whether or not a distribution is Gaussian, and or like whether or not a Gaussian process is, or a stochastic process is Gaussian, and this is essentially what all of the proofs are based. Yeah.
Sorry. So when you these are random unitaries, do you have a specific setting in mind, like a shadow kind of setting where you have random circuits, or something else?
Like typically, yeah. I mean, often it's not like a specific choice of circuits. I mean, this should come from like the task. So like the actual transformation that you're actually trying to model with your QML model, right? I mean, it could be some like some circuit class that might correspond to a some like dynamical Lie group. But yeah.
Okay.
Okay. So yeah, S. So yeah, and connecting this now more to the prior of the learning problem. What I mean, this is what comes from the probabilistic interpretation of our assumptions. we know that if we now use this this process as the prior and it is Gaussian, using exactly a Gaussian process as the model is a faithful choice, right? Because we know by construction, so to say, that this this model then aligns with our assumptions, and we also from the assumptions already know the correct kernel choose. So we have a specific expression for the kernel based on our assumptions, and that's what we call a provable quantum Gaussian process. Now, for a concrete learning instance, this there would be a instantiation of this U, right? It would be fixed, but we do not know U. This is why we do the learning in the first place. And this means that then the learning of the, or like the training or conditioning of the quantum Gaussian process learns the action of this particular choice of U from the data. Okay, so as an example, like it's almost a trivial case is that the global unitary group is a subgroup of the global unitary group. So this means that we would assume that in the setting in the QML setting we are trying to model, this unknown transformation U acts on all of our n qubits. So this essentially almost saying that we do not really impose much of an assumption there because this is true for any closed quantum system. And then it was shown that for the unitary group and, for example, a Pauli string observable, asymptotically this stochastic process will form a Gaussian process, and with mean 0, and here the kernel function is contains the fidelity of the two input states, and then up to some normalization that comes from this normalization factor here, and the norm of the observable, which is just the same for all Pauli strings. This is just the quantum fidelity kernel or overlap kernel. And yeah, this was shown in this paper here. And yes, so they showed that this actually forms a quantum Gaussian process. So choosing the global unitary group as our assumption provides us with a provable quantum Gaussian process. Yeah, so the more generally, the form of these kernels is like this. So we have overlaps in these subspaces that are defined by the operator space decomposition that we get from the group G and the specific subset that O lies in. Yeah, I just want to mention this, but I think I should continue in interest of time. To the scalable part of this theory. So
questions about what you just said. So if I understand correctly, so the goal, so you have a bunch of states, Roti, that evolve through a unitary that is fixed but unknown, and the goal here is to retrieve, to reconstruct the unitary itself, right? Mm-hmm. And the way you do it is you compute kernels at the end.
Mm-hmm. Yeah.
It doesn't matter how you compute them, because you need to compare different states, right? So you evolve Roti, you evolve Roti prime, do a control swap or something like that. What do you have in mind with this?
Exactly. I mean, it matters. The choice of the kernel matters. here, because it will tell you what information of these of your input state is actually relevant, right? Because by knowing this like subspace decomposition and the relevant subspace selected by the observable O, we know that any contributions of these input states or like projections outside of these subspaces is irrelevant and will not influence the observable.
Okay.
Or like will not influence the output.
But
Because-
physically, what kind of, so every state evolves independently through the unitary, or like you
Yeah.
hold a couple of them, and because if you want to compute the kernel of states that evolve through the unitary, you know,
Yeah, I mean,
you need to hold a couple of them and then compare them coherently or something like that.
Yeah, I mean, they don't, for the kernel, you don't have to run them through unitary, right? So the kernel is computed only on the actual input states. All right.
Right. Okay.
Yeah.
Okay.
Because the exact unitary then is, or like the concrete instantiation of the unitary is unknown, right? So we cannot use this information to construct the model, but this is exactly then where the data comes into play. Because this will
So the information you use is the overlaps of input between input states, and then you use the output probabilities, I guess, or output expectation values compared to with respect to some observables. Okay.
Yeah.
Okay.
Okay. So yeah, what we now need for the scalability, in addition to these assumptions that we use for provability, is on the dimension of these subspaces. And this is here that the dimension of these subspaces has to be bounded by a polynomial in the number of qubits n. And this is exactly where this global unitary group assumption falls short, because such an action on all of our qubits and of our qubits would not be scalable, right? Because here this like subspace that we obtain where our Pauli observers lie in exhibits a dimension that is exponential in n. And this is in some sense something that is expected from results that the general like fidelity kernel suffers from exponential concentration phenomena. So what we can do is that we instead restrict and now go for a non-trivial subgroup of the global unitary group, which would be a unitary group restricted to a subset, so like only a few qubits. And more precisely, we would restrict it to a subsystem of size that is logarithmic in the number of qubits. And also the observable then would have to be restricted to only have support, or like to only non-trivially act on this subsystem. Right, so it could be a Pauli in these m qubits instead of a global Pauli. And then this dimension is bounded again by a polynomial. And this means, yeah, we get a scalable QGP, and the provability carries over. It doesn't really matter that we reduce the system size here. And this brings me overall to a overview of assumptions under which we get both provable and scalable quantum Gaussian processes. So we see that that for the unitary group, for the orthogonal group, and for the symplectic group, we get provable QGPs, which is based on previous works. But for the scalability, we always have to restrict them to act only on very few qubits, in particular to this log size subsystems. And this is why you would naturally ask, is it possible to have a provable and scalable QGP where the unknown unitary would act non-trivially on all of our qubits? And that's exactly the main theoretical contribution of this work, which is on using the match gate group or the free fermionic group. Which now brings me to the to the second theory part. So what are match gates or free fermionic transformations? They are most easily defined by Majorana operators, which by the Jordan-Wigner mapping are correspond to n-qubit Pauli operators, like this, and they have this anti-commutation property. And why are these Majorana operators useful? They're useful because they induce the group of match gate circuits by the exponential of such quadratic Hamiltonians. So just products of two Majorana operators. And as a concrete example of what match gate circuits are, they can be, for example, generated by these Paulis here. So we can obtain them by gate sets where we have Pauli Z rotations, single qubit Pauli Z rotations, and 2-qubit Pauli X rotations on neighboring qubits. So this, for example, is a complete set to generate match gate circuits. Just to make sure that it's not like a very contrived thing. These type of circuits come up in practice. And then so these unitaries form the representation of this Lie group, which is actually the double cover of the special orthogonal group. I will skip some details here, but importantly then we have this decomposition into these subspaces or modules under the match gate group, where each of these subspaces, we now label them with M, is spanned by products of M distinct Majorana operators. And then their dimension is given by this binomial coefficient, which is for constant for constant M. This is upper bounded by a polynomial in N. And yeah, because I would really want to talk about the applications, I think I will quickly mention that they are provable under some conditions. Here is the form of the kernel as expected. We so given that our operator is in one of these free fermionic modules, we to compute the kernel, we project into this module to compute the overlaps. We also actually have a device, a protocol where we can directly estimate these module overlaps. And now I said under some conditions, and actually, these conditions depend on so there's some case distinction based on the type of, based on the module that we consider generally, and then for specific conditions or like families for these input states and observables, we obtain that, or we can prove that QGPs either emerge, or, which is very interesting from a physical point of view, can be proven to not emerge. So even then, asymptotically, the moments wouldn't line up with the moments that we need for a Gaussian process. And we have cases where we can either guarantee for a certain family of states, say, that the Gaussian process emerges or that the Gaussian process is ruled out. But yeah, so and yeah, as I mentioned before, we have a protocol, and like everything is is scalable as long as you consider m to be constant. But yeah, I now really want to get into the applications. So we have the nice thing about Gaussian processes, we can use them in a lot of different applications, not only in regression. You can also use them in classification and optimization. And in our work, we demonstrate this on synthetic data sets, but also in physical models. So as one specific objective in regression is extrapolation. And this really well highlights how important it is to have inductive bias in your model. So for this, we consider a 50-qubit synthetic data set. We prepare these data sets row with 2 layers where T is used in rotation gates. All of these rotation gates have different frequencies, which we randomly sample but keep fixed then from a normal distribution. This is just to make sure that these rotations are all like the frequencies are you know they don't line up, and we get actually a more complicated behavior. And then yeah, we use nearest neighbor CNOT gates for the entanglement. We assume that we have a random but fixed match gate, or like we sample a match gate circuit and keep it fixed, and then O is a Pauli string in this first free-forming module B1. So this would be just any single Majoran operator. So now, concretely, this is how the ground truth looks like. We have this rather complicated looking function that we want to model. And now for extrapolation, this means that we will restrict the training data to a small region, here from T being from 0 to 1. We have 15 training data points. And then for testing the model, we make predictions to larger regions, so all the way up to T equals 10. So now, because I said this is for extrapolation, it's very important to have a proper inductive bias. Let's for now assume that we ignore the knowledge that we have about the system, so that it's match gate and the module of the observer. So this means we assume no prior knowledge. So it could be any global unitary transformation, right? So this means, okay, we just choose the corresponding unitary like fidelity kernel. So just use the fidelities. And then this Gaussian processor, this kernel obviously lacks an inductive bias. And I will not involve shot noise for now, just to make sure that it's clear that the collapse of this model is not just due to finite precision errors. But yeah, so this is what we would get. So while the interpolation is somewhat successful, so like, predictions between the training points, but it's also trivial because these training points are very close to each other, the extrapolation really fails, right? So like once we are like just a bit away from the region that's covered by training points, our Gaussian process just like resorts to the prior zero mean prediction, and accordingly the uncertainty blows up. And why is that? So if you look at the kernel values here represented as this kernel matrix, this heat map, if we pick 2 points that are close to each other, this means we are essentially almost on this diagonal, which has larger values for kappa. But once we step further away, we are in this region of the kernel where in this region where the kernel values are 0, which means that there's no information gained or like shared between these two data points or like these two quantum states at Ti and Tj. And this is why, yeah, the Gaussian process cannot use any training data information, has to resort to this zero mean prediction.
Sorry, so to clarify, this is still without statistics, right? Notion noise.
This is without noise, yeah.
Okay.
Without shot noise.
So if I understand correctly, so you're saying this doesn't work because the training states do not sufficiently span do not sufficiently cover the space of relevant states, right? So you're saying in the test, even though projecting on this particular observable, it looks like training already saw a specific value of the expectation value, the underlying state might be very different on the right side of this plot, and therefore, okay. But you would expect this to work if instead in the training state, in training data, you had like a sufficiently expressive set of states, let's say states span the space, right?
So what's the last part?
So if the training states are, I mean, that will require exponentially many, of course, but if the training states span the space of all states, or let's say are expressive enough,
exactly,
you would expect this to work regardless, right?
Yeah, and this is what we can see here in the interpolation, right, between two training points, right? So any point between two training points, or any of these states is not too far away from the training points. So there they have enough similarity, right? Like high enough overlap to inform each other. Yeah.
Okay, and so if instead you consider basically a prior on the actual unitary you might be sampling from, then you manage to generalize, extrapolate.
Exactly. Yeah. And this is what I will show in a second or now.
Okay.
Yeah. So if we actually use this knowledge that we have, which is it's a match gate circuit, and it's a the observer is a Majorana operator, and we use the corresponding match gate kernel. Then now we have strong inductive bias, so we have a physics informed model, and as you can see, we can perform exact extrapolation. So here, I mean, this is still without shot noise, and without shot noise, this data completely suffice to perform the extrapolation. And if we now look at this kernel matrix, it also becomes clear why only a few training points suffice, because now even for states that are further away, we still have kernel values that have a high magnitude, right? So this means they're like, I mean, either positive, so like they're highly like correlated, or
and the only way you use this prior is through the choice of the kernel metrics, right? You're saying
exactly.
Basically, the way you compute this fidelity, projected fidelity kernel.
Exactly.
And then the scale is there.
Yeah.
Okay.
Because now, we are projecting these states in the subspace, and even though these states, far away states, have barely any overlap in like in terms of like their full fidelity, within the subspace they might have high overlap. That's exactly the key here.
This is projection on this space spanned by the observable, right? So in this form of kernel, where does the space of possible unitaries enter? Or is just the fact that if the unitaries are sampled from spin, then you can use this kind of approach?
Yeah, it's I mean, because this you said the subspace is spanned by the observer. I mean, this is like, it's not like only the observer, but it's like the subspace that is then also like preserved under the action of the unitary.
Okay.
Right. So this is important because you don't know what exact match gate circuit is being applied, right? So effectively, it could be any observable, or like the observer could be any operator in this in the subspace B1. That's why you have to project into this full subspace. Yeah.
Okay. So you said, maybe I don't remember, B1 is the space. How do you define B1 again? Sorry, because maybe I'm not remembering.
Yeah, sorry, I was a bit fast with these definitions, but yeah, B1 is for the match gate assumptions. B1 is the state that's spanned by all of the Majorana operators.
Okay. Okay.
Yeah. So it's the dimension is 2n.
Okay. And
Okay.
this aside, the training is just the usual. You do the pseudo inverse, or maybe regularizing. You invert the kernel matrix, and then you multiply by the
Exactly. Yeah, I mean, this is the nice thing about Gaussian processes in general. There's no like the only information that we have to gather from the quantum device is the kernel, and then after this everything is happens classically, right? Yeah. And yeah, it's just like the inversion of the kernel matrix and stuff like this. Okay. And then yeah, even if we apply shot noise, so you have like 1,000 shots for each observation, each training label, and 10 to the power 5 shots for each kernel value. The quantum Gaussian process is still robust, and we can achieve this extrapolation. So like saying that the mean already still captures the overall signal, and even in regions where it does not exactly capture the signal, at least we get wider posterior bands, like which reflect the additional uncertainty. And yeah, one could improve this by adding more training points, of course. Okay. So now is the second application I want to talk about. This would be on that is on predicting phase diagrams. So now we would go from this synthetic data set to a data set that's actually based on a physical model. On the states would be ground states of a physical model. In this case, we look at the bond alternating XXX Heisenberg model on 50 qubits. So this is just a one-dimensional chain, which is non-uniform because we have alternating bond strengths. So like there's a different strength for the odd bonds and a different strength for the even bonds. And in the thermodynamic limit, there is a phase transition exactly in these strengths. Bond strengths are the same. So this ratio is 1. And we can define a regression task on this by trying to predict the corresponding order parameter. So here for this, for a finite system, you can use a proxy for this order parameter, which is where you go in the where you measure at the middle of the chain these pair of Paulis, and this is essentially this corresponds to using a swap operator as the observer. It's just like it missed the identity term. And we can also use this for a classification task by just using the two labels, or like the two phases as labels, because we know from the thermodynamic limit where the phase transition is. So here for this observer, we have this. We know that the Pauli X and the Pauli Y terms here lie in the second module, and the Z lie in the fourth module. So again, the second module, like B2, is spanned then by it's a space spanned by products of two distinct Majorana operators, and B4 is the space spanned by products of 4 distinct Majorana operators. In this scenario, we don't apply any transformation. So it's like, so to say, a trivial instantiation of a match gate circuit. And then, yeah, since we are now dealing with a observer that falls in 2 modules, we build our kernel